Hi everyone. Can you hear me?
Yes, sir.
Okay. Yeah. So we'll start the session then.
Yes, sir.
I hope you can see my screen. Okay. Yeah. Start. So this week, uh, the focus was on key point, rather features, feature detection in images. Yeah. So based on that, we'll have a few questions discussed today. Okay. So how was this week's lectures? Did you find them easy to follow?
Not much, sir.
Okay, okay. Yeah, I mean, the feature detection is something, I mean, these are handcrafted features, so most of them are based on some, I mean, some background, some maths background that you have seen, but most of them are heuristically built. So it's mostly empirical that you see rather than there's some mathematical background out there. Maybe that's the reason it's not so super clear on how or what to choose in which places. Anyways, yeah,
Yes, sir.
yeah, we'll start our discussion. So this is the first question. The gradient along x and y directions is given by this thing. Uh, I mean, it's just the pixel differences. Yeah, pixel differences. Yes, it's the pixel differences based on. I mean, you move one position ahead and one position back, and then take the pixel differences. This one is in x direction, and this one is in y direction. That's all. Okay, so they are just defining how to compute gradients. The top left corner of the matrix is considered as 1 comma 1, so they are just giving in indexing that this is 1 comma 1, and here if you move, you vary the column, that is 1 comma star, and here if you move, you vary the row, which is star comma 1. Okay, so it's similar to what we have seen in the earlier sessions. So we are given a matrix. We need to compute gradients. The gradients are defined by ix and iy along x. I mean, for x direction it's given ix, and for y direction it's given iy. At the center pixel location a. Okay. So how should we proceed? So it's simple, right? We are given the formulas I x I plus 1 minus x of I minus 1 by 2. So here for central pixel, what is it? Our I is what? 2, j is 2, right? So this is 2 comma 2 given the convention. So based on this, it's pretty straightforward. So Ix will turn out to be, this is zero point 0.3, this is what, x of I plus 1, right? So we need to move in x direction one place ahead and then take the value, which is I plus 1. So it is zero point 0.3 minus x of I minus 1, which is zero point 0.4 given the central pixel location, which has zero point 0.2. So based on that, it's zero point 0.3 minus zero point 0.4 by 2. And similarly for IY, it is, sorry, it is what?
Point 0.7 minus point 0.4.
Yeah. So this turns out to be 0.05, and I guess this turns out to be 0.15. Yeah, the first question is pretty simple. Any doubts in this question? Okay.
Will there be a chance of like asking what will be ix and iy for the one position, like point 2? So the I minus xi minus 1 would be not defined. So we need to consider 0 or what?
Oh, you're saying that if we are in some weird position, like if we take this as a central pixel,
Yeah.
so there are many methods to it. Generally, what we do is we consider these as zeros and we consider this
Okay.
part of the matrix and then we proceed.
Yeah. Okay. Thank you.
Okay, so move on to the next question then. Did something wrong, it should be minus 0.05. Yeah. Um, okay, so the next question is somewhat related to what we saw in the last few lectures. Okay, so which of the following is true about Harris corner detector? Okay. What is Harris corner detector? Does anyone remember? So, okay, so first I'll read out the question. The first option is Harris corner assigns a feature descriptor to each corner points of for feature matching. Do you think it is right? Okay, I guess no clear view on what's Harris corner detector. Okay, let's first understand what is Harris corner detector. Can can you revise what's that? If you are able to recall it, then these points will be clear which one is right. So for the previous lectures, what was our focus on?
Projection matrix, like
Sorry, what?
a projection matrix and all we learn.
No, no, no. For the last
Like
week lecture, for the lectures in the last week.
stereo geometry.
No, 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 no. Last week in the sense, okay. So we have still not crossed the week. For the week 6, the current week which we are going on. So what was our
Feature
focus on?
detector.
Yeah, feature
Feature
detector.
detector and
What kind
description.
of feature detectors did we focus on?
Corner detector.
Uh-huh, sorry.
Edge and corner detection in the image.
And
Description of the like the edge and corner.
okay, feature detection and description. That's what our focus was. What? How many types of feature detection and description where we looked into? First is the point one. Point. I mean, you are trying to find a single point in an image and get its featured. I mean, detect it first and then describe it. So I would say it has point features, point feature detection and description. The next one.
Edge.
Uh, yeah. I mean, we did something called as region and texture description, if you remember. So for region and texture description, yeah, there were many multiple things like HOG, LBP. These are all based on region and texture description. And the third one, third one is what? Image global description, right?
Yes, sir.
Yeah. Okay. So first we have to need to have this clarity that what did we even learn. So we try to learn these three different kinds of feature detection and description. So first is the point feature, where we try to assign a feature to each individual pixel, not each individual pixel, but a few specific pixels which are of interest. Next is the region and texture description, where we consider a region of a image and try to get the texture information based on the descriptor, or rather encode the texture information in the descriptor. And the third is the global description of the image. That means one vector, we are trying to find a vector which will represent the full image in total. Okay. So given these three things, which category does Harris Corner fall?
Point feature detection.
Yeah. Okay. So at least that's good that we have that clarity. So it's mostly for the detection part. There is no description out there. So Harris Corner is a detector, first of all. Is a detector and not a descriptor. So based on these things, now do you think the first point is correct? Harris Corner assigns a feature descriptor to each corners for feature matching.
No, sir.
Yeah, because we don't really do any kind of description out there. We just find the point and that's it. Harris Corner finds key points based on significant changes in intensities along all directions. Do you think it is right?
Yes, sir.
Why?
Because the corners are detected based on the intensity.
Okay, can you tell me the procedure? How, or whatever was given in the lecture? I mean, the basic steps on how this works. If you remember the basic steps, then it's pretty clear that yeah, it's true that the key points are based on significant changes in the intensities along all directions. So how do we start with it? If you remember anything, so we check for uh, what differences in image pixels over patch over a patch. Do you remember this? Something called as EUV. So these are the exact notations that were used in the lectures. So I'm just using it. So what does it even mean?
We will consider a window and will slide like if the window is changed from XY location to UV location, then the intensities that were present, like that were in the window at the beginning, and the intensities measure like after U comma we change both the intensities will be like will check the difference between those intensities.
Mhm. So
And
here it's like we fix U and V for a given U and V. We go through the whole window. That's what this thing says. So once we go through the whole window, what do we see? We check for differences in the image pixels over a patch. That's all. So for u comma v, mm, so yeah, for every pixel, this is for every pixel in the image, we do it separately. So you consider this window. I mean, some window which is of size probably 3 cross 3, 5 cross 5. Generally, we take odd numbers and we just try to get the square of the differences. That's all. So based on this, what do we get? If you remember that we approximate here rather with a first order. I mean, it's a first order approximation. I of x comma y plus,
Do I?
yeah. So it's nothing, just the image derivatives I x and I y. So is this thing clear?
Yes, sir. So the window is acting as a pixel, or we'll say take a separate window and slide it from top left to bottom right.
Uh, yeah, yeah, yeah. So sliding means you are changing this u comma v. For a given u comma v, this window is fixed, right? Sliding means you are going through the. Okay, some noises out there. Sorry. So for sliding means you are changing u comma v. Once you fix u comma v, you are fixing the window position. That's all. So within a window, you are checking all these properties.
Okay. Like when we consider a whole image, how can we like how is it working?
Okay, okay. So if we have the whole image like this, so when you say
Yeah.
sliding, so you change the central pixel. Central pixel is u comma v, and the other pixels here are x comma y.
Okay.
That's all.
So for all the pixels, we'll consider the
Yeah,
center
yeah.
as
For all
a
the pixels,
x
you will
Okay.
compute this e separately. Okay. So for every pixel in the image, that's what I'm saying. That every pixel in the image, we compute this e separately. Based on this, we do a first order approximation. And given this, we can easily cancel these two things out, which gives us what, this is ix, iy, uv. So this is a matrix, and this is a vector matrix of probably 2 cross, cross 2, and this is 2 cross 1. Yeah, you have two columns and ix. Sorry, sorry about this. So this is a single vector, row vector. It's a 1 cross 2. Ix is a single quantity, iy is a single quantity, and of course uv is a single vector. So based on this, what do we do? So we just try to expand it based on linear algebra, and this is what we get. So we have uv, ix, iy like this, then ix, iy like this, and uv like this. Are you clear about this thing? The expansion?
Yes, yes, sir. I
Okay,
understand.
yeah. So it's great. So since this summation only depends on x and y, we'll take this summation inside, and it will look something like this. Okay, I just write it like this. So for every pixel in that window, you have to, I mean, take the image gradients and then do a outer product of those image gradients, and then sum it up. So this whole thing is the matrix H, which captures the statistics of the statistics of the patch. So based on the patch, you will define whether this is a key point or not. Okay. So if lambda 1 and lambda 2 are eigenvalue eigenvalues of h, since h is 2 cross 2, so we'll only have two eigenvalues. So if you have two eigenvalues given as lambda 1 and lambda 2, based on the properties of lambda 1 and lambda 2, you will decide whether u comma v is a what key point or not. So this is the whole idea. So how will we decide?
Uh,
Yeah.
is it u comma v or x comma y?
No, x comma y are the variables over the window. So here u and v are the variables which are the image which are denoting the central pixel.
Okay.
Yeah. Okay. So based on u comma, I mean this H matrix, we decide whether u comma v is a key point or not. So for this, the function that Harry specifically uses is lambda 1 lambda 2 upon lambda 1 plus lambda 2. I hope you remember that. So this is nothing but just the determinant of H upon trace of H from the matrix properties. This part is clear. So in general, uh, this would have been told in the class probably. So if you have something like this, if you have a region here, if I plot lambda 1, lambda 2, so here I assume that lambda, okay, here
Lambda 2 is greater than lambda
much
1.
much greater than lambda 1, here lambda 1 is much greater than lambda 2. Okay, so these regions corresponds to what?
Edges.
Yeah, because only in one direction there is large variance, the other direction there is no variance at all. If you remember the simple pictures that were shown in the class. In this is a flat region. So this is the center 0, comma 0. This is the flat region where both lambda 1 and lambda 2 are low, and this specific region, this region, this is
Corner.
yeah, supposedly corner. I mean, there can be cases that they cannot be a corner, but mathematically speaking, this is the region where you have corners, where both.
Maybe curves will come, I guess.
No, there are outliers. I mean, there can be cases where it seems like a corner, but it may not be. So, what do you mean
Okay.
by corner?
When two edges meet.
Okay. Anything more? What if two line segments meet at a point? Okay. So you say that this is a corner, which is correct, of course. Any other definition of corner? For instance, if I have some structure like this, these are all corners, right?
Yeah.
So these are all corners. So you don't. I mean, of course, here you say that two edges meet. It's fine, but what if there is a diagram here, a painting here, some painting uh, which has some, how do you put it? Maybe a painting of pyramid. So this is not a real corner, right? This is just a painting,
Yeah.
but this is still considered as corner because it just measures the changes in the intensities. This corner
Yeah.
detector. Yeah. So even this is a corner for us. So whatever you see perceptually as a corner is a corner here, and not it may not resemble to something in real life. Okay, so that's fine. So where are we? So given all these things that we know, so if lambda 1 and lambda 2 are high, That means there are significant changes in both the directions, which means that this is right. Okay.
Yeah.
Okay. So the next one is this Harris corner. Okay. The next thing is Harris corner uses gradient along x-axis only. Do you think is it right?
No, even y-axis it will
Yeah. Yeah.
consider.
So in general, it considers both the axes. It needs what significant change in all the directions. So it cannot be limited to just one axis. What about this? Harris corner replaces each pixel with the frequency of occurrences of that plane in the sliding window.
It doesn't replace anything. It just finds the change in intensity.
So what is it right or wrong?
Wrong.
Okay. I hope this is clear. Any doubts? Harris corner doesn't do anything with the image. They just, yeah, I mean, decide which are the key points of the image. That's all. So
Is it possible to like based on general programming skills, can we implement Harris corner on our own?
Harris corner in your phone, you want to implement that?
Like on our yeah, I thought of implementing.
Yeah, it's actually pretty lightweight. You can do it.
Okay, okay, I'll look into it.
I mean, there will be existing implementations for sure, I guess, but maybe you should just try first on a laptop and then try porting it on your phone.
No, I said on my own.
Oh, on your own. Okay, okay. I heard phone.
Yeah,
Sorry about that.
no, no, okay, no problem.
Okay, yeah. So this is fine. Okay, great. So I'm just trying to relate a few things with the maths, limited maths machinery available here for our feature detection and description. Hope this helps understanding it better. Where am I? Yeah. So, okay, we have read about shift. What do you mean by shift? What is the full form of shift? Uh, is it that hard to remember? Shift is what? Scale invariant feature transform. Am I right?
Yes, yes.
Okay, yeah. Hopefully I'm right. Yeah. Okay, so based on this, so we have some question on shift operator. So here we are talking about the detection. Yeah. So first we are yeah here this question belongs to the detection part. So if an octave in shift operator has 12 images, then the scale factor by which each image in octave differs from the next image is what? So first of all, what do you mean by octave?
Shape having 8 points.
Sorry, what?
Octagon.
No, no.
Okay.
Anything from the slides that you might want to refer to? Okay. So So this is something that was given in the slides. I hope you remember that. Ah, okay, so what's an octave? I hope this part is visible. This is the first scale octave and this is the next scale octave. So, I mean, in general English, octave means there should be something related to eight number, I mean, eight instances. But here, specifically, what we mean is we try to change the scale of the image, right? So before changing the scale of the image, it's the number of. I mean, this whole thing is. called as an octave. So one whatever operations you do on uh, in the first scale, you call it as octave. Again, in the next scale, whatever operations you do, you call it as another octave. So if you remember that we take difference of Gaussians in shift feature extraction itself. Yeah, because we want to work on different scales. So how do we downsample then the scales? You cannot directly downsample the images just by taking alternate pixels or every fifth pixel or something like that. Do you know why? Why? Because we have aliasing artifacts. Uh, if you remember that in our first week or yeah week one we did some image processing. We tried to learn about some low pass and high pass filters, right? So our sampling should be based on Nyquist criteria. So if you don't have the images in the proper Nyquist, I mean the frequency range is higher than the Nyquist criteria, you have to remove those frequencies before even trying to sample the images. So based on that idea, we first try to do convolve with Gaussian, which is what Gaussian is what Gaussian blurring is a low pass filter. So what it does is uh, it removes
Noise.
noise is okay, but if what if there is no noise? Removes high frequency components, right? Because it's a low pass filter. That means you get a blurred image. But why do we want to do this? Because we want to get everything over the scales. We want to find some descriptor which is defined over the scales. So for that we need to find different scales of images, and for that we need to downsample. But before downsampling, we need to do some convolution with low pass filter. Here we choose Gaussian as the low pass filter. Okay, so this is how it's linked to the signal processing theory or the image processing theory. So what they do is they um, so they convolve with Gaussian in such a way that uh, so the blurring factor is k. Okay, so if you have n images in okay, so for our question, what is this? If you have 12 images, so for instance, I mean for this case n is 12. So for each of these octaves, each octave has n images. That and remember that this is the original size image. This is the original image. Okay. So given that this is the original image, how many times did you convolve it with Gaussian before downsampling it? So if you see that we are convolving it with Gaussian recursively, right? Until we downsample. So if you have n images, so if all of this one this is one two dot 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 n images, then how many images? How many times did you
N
convolve
minus 1.
n minus one? Yeah. So n minus one. Uh, yeah. How do I put it? Okay. Yeah. N minus one convolutions are performed before
Downsampling.
downsampling. Okay, so now it's easy, right? So if you have something, so for each time you are convolving it in such a way that the blurring factor is k. Blurring factor is k means here k will be of some order of pixels. For instance, 1.2 times, or we need to find k ultimately. The scale factor by which each image in octet differs from the next image. So we are trying to find the scale factor k. So k is the scale factor. So what do we know till now? That we applied that scale factor how many times? N minus 1 to reduce it by a factor of 2, right? Or you can put okay, just a minute, someone joined. Okay, so you can think of it like this way. So we uh, recursively apply this k n minus 1 times, so that the effective scale factor is 2 after n minus 1 recursions. Is this clear? Is this statement clear? Okay. So we apply the filter recursively by a factor of k, so that the net effect is, so the net factor is 2 recursively n minus 1 times. Is this statement clear? So we are trying to apply a filter of with scale factor k n minus 1 times, so that our net effect of the scale factor, so that our net scale factor is 2. So since now your scale factor has crossed 2 pixels, then what can we do? We can downsample the image. That's what it's done here. Okay, I hope this part is clear. If there are any doubts, you can
It
please.
will reduce the image size, right? The
Yeah,
two.
yeah, yeah. So it's like your blurring effect should be such that it crosses 2 image pixels. So as soon as it crosses 2 pixels, we can just downsample it.
Okay.
So that's what it means here. So that's what I'm writing it here mathematically. So k is some scale factor that we are trying to, I mean, that we are trying to find. 2 is the net effect after which we will downsample the image, and n minus 1 is the number of times you have applied the filter. So it is, so what will be k? K is simply 2 to the power n minus 1, which is 2 to the power 11, 2 to the power 1 by 11. Okay, which turns out to be 1.065. So effectively, what it means is we are trying to reduce the image by 1.065. Reduce the, yeah, image by 1.065 times in every convolution. But since it is discrete, we will wait till the time its effective scale factor is 2. Once that's done, we'll downsample it and then we'll continue it over here. Is this part clear on how Sift works, or rather how these pyramids are generated? Any doubts? Okay. So yeah, once you downsample it, you can just find the extrema in this 3D DOG space, the difference of Gaussian space. And if you choose this particular scale, which has maxima, that gives you the exact scale which is given for the shift feature. question. Okay, the top left corner of the matrix is 1 comma 1 and intersects increment for x and y axis along the horizontal right and vertical downwards. So yeah, that's what the convention being followed till now, and it's the same. So we are given a matrix A. We need to compute the magnitude and orientation in degrees using the first order difference operator at the central pixel. So what does it mean? What is the first order difference operator? It is this, right? Whatever we are doing till now. Fx of, I mean, sorry, ix is fx at I plus 1 comma I minus f of I minus 1 comma y, and I
divided by 2.
divided by.
2 in ix.
Okay, okay. So here, uh,
Ix is 0.3 minus 0.5 divided by 2, right?
okay, okay, okay. Now that's okay. So here we are only using the difference operator. We are not taking any average.
Okay.
Maybe I'll just change the notation. I guess that will be better. I'll just write as dx. Dx is just the simple difference, and dy is another simple difference along uh, y direction. Y I plus 1 minus f of x I minus 1. Okay, so we'll just place the values here. Dx is what? Zero point 0.3 minus zero point 0.5, which is minus of 0.2. Here it is zero point 0.3 minus zero point 0.1, which is zero point 0.2. Okay. So given these two things, we need to find the magnitude and orientation. Orientation is just the angle. How do we find it?
Orientation is the angle made with the x-axis.
Okay, magnitude.
I wasn't able to understand it.
Okay, so magnitude is just the
Square.
Euclidean norm of dx dy. That's all.
Okay. The L1 norm, L2 norm, LP norm,
L2
right?
norm. L2 norm.
Okay.
So since you are in two parallel perpendicular directions, right? So magnitude will just be the Euclidean norm.
Always L2 norm.
Yes, generally
Okay.
speaking, yes. So it's what does it give? It's like point two minus point two square plus point two square under root. So it is point two root two, and root two is what? 1.414, which is 28. You have this magnitude and direction. What is the direction? Direction is some theta, which is tan inverse of dy by dx, which is tan inverse 1, which is what? Pi by 4, right? Pi by 4 radians, or 45 degrees. Is this fine?
Yes, sir.
Okay. Yeah, this was pretty simple question. It's just that we need to understand what's the difference operator. That's all. We are not taking any derivative here, so it's just a difference operator. So simple differences. Okay. We'll move on to the next question. Okay, some Which of the following is true about shift operators? Gaussian pyramid is used to make it scale invariant. Is it right or wrong?
Yes, sir.
Yeah, we just discussed it now. Yeah.
Yes.
It can handle changes in viewpoint up to 20 degrees out of plane. What do you mean by out of plane?
Maybe the objects are tilted towards,
There is
like,
no object being tilted. You always tilt the camera, right?
yeah.
So then what does it mean? So if you rotate an object like this, do you think it's an in-plane rotation or out-of-plane rotation? Sorry, if you rotate the camera like this, it's not an object. Sorry, where O is the camera center. Do you think it's an in-plane rotation or out-of-plane rotation?
In plan? Oh,
Sorry, it is out-of-plane by the way. What is in-plane rotation?
uh, maybe the
So it will just rotate here itself.
yeah.
So your principal axis will be the same. In plane, the principal axis will be same. So you're rotating about principal axis. You can think of it like that. I mean, it's physically exactly the same. Maybe you don't have to think about it. Here, the principal axis will differ. Okay, so I hope this notion of in plane and out of plane rotation is clear.
Yes, sir.
Okay, so now can you answer this? It handles changes in viewpoint up to 20 degrees out of plane. Yeah, the answer is no.
No.
60 degrees. It can handle up to 60 degrees.
Okay.
So, of course, now it's not like there is a proof for it. It's empirically seen that it can handle up to 60 degrees. That's all. Is it rotational invariant?
Up to some extent. Right?
But in general, is it the case?
So rotational means like again 2D or 3D.
So, yeah, in plane rotation is the 2D rotation. That's what is here it's been referred to.
Then it is yes.
Oh, okay. So, you think that it can handle in plane rotation? To some extent, yes, but in general, no. Okay, that's the answer.
Okay.
So why I'm saying that to some extent it's yes, because we have an orientation defined out there with the histogram of directions, right? Magnitudes, histogram of the yeah. We'll do a next question out there on histogram as well, so that will be clarified. So we build a histogram, right, and then we choose a canonical direction. So the one which is highest is the canonical direction, if you remember that. So since we are fixing some canonical direction, it makes it somewhat invariant to rotations because our canonical direction will rotate exactly if you have that in plane rotation. But the whole point is it doesn't necessarily lead to a rotation invariance operator. Okay, so the last part, the dimension of the description vector is 128. Is it right or wrong? Hmm? What's an easy way to remember it? So we take a patch of 16 cross 16, right? So once we have a patch of 16 cross 16, what do we do next? We divide it in 4 cross 4 patches, right? Or rather 4 cross 4 cells as given in the lectures. So within each cell, what do we do? Within each cell, we get the magnitude of the 8 directions, right? So that means total how many directions? 4 cross 4 into 8, which is 128 dimensions. Are you fine with this?
Yes, sir.
Okay. So ultimately it has the dimension of the description is 128. Okay. Since I told that we'll have our next question based on the histogram, so let's do it. Okay, the histogram contains 9 bins corresponding to the angles 0, 20, 40, 60, 80, 100 to 160. So we have some histogram which has here 0, 160. Okay. So given the magnitude and direction in degrees as matrices as 3, 5, 1, 8, 18, 80, 40, 20, 10. Okay. So what does this mean? That at 80 degrees the magnitude is 3. This is the direction, this is the magnitude. What is there? 40 degrees our magnitude is 5, 20 degrees magnitude is 1, and 0 degrees the magnitude is 8. Okay. So here the magnitude is 8, 20 degrees the magnitude is 1, 40 degrees magnitude is 5, and 80 degrees the magnitude is 3. I hope this diagram is clear. This is the direction and this is the magnitude. That's what is giving us the histogram here. So compute the vector representing the histogram of gradients corresponding to the details given. What would be the vector?
Option A.
Yeah. So it's just 81503 and then zeros. Yeah, it's option A. Okay. I mean, this is how the descriptor part is made. That's why to understand that part, this question is given. That's all. Okay, we move on to the next question. Okay. Since we have done too much of point features, we might want to move to texture kind of features at this point. Okay. So consider a 3 cross 3 neighborhood with grayscale pixel values, okay, given in the matrix A, and we need to obtain a single local binary pattern. Okay. So what is local binary pattern? Hmm? So we have some central pixel. We decide a neighborhood pixel x comma y. X comma y is in the neighborhood or in the window. So let's call the central pixel as p. So if I have a function tau p with x and y, and I'll not write it as p. Sorry, I'll use the original convention that we were using. It will be better. So the central pixel is u comma v, and then we have a neighborhood pixel x comma y. So if the pixel value at u comma v is less than pixel value at x comma y, then we assign it as 0. So this tau function will give us a binary value. Okay. So what are we given in this question? We have some matrix A as 82. Okay. So we have this matrix A. So first we'll find this tau of A. Given the central pixel at, I'll just write it as 2 comma 2 as our usual notation. So what does this mean? What is 80? 80 is less than 192. So we'll put it as 0.
0,
Yeah, if it's more, then we put it as 1.
1.
That's all. 0. For equality, we are not defining at this point. So we'll leave it as blank. I'll leave it as a blank here. Since we don't need it for computation as well. 100 is 0. This is 0. Oh, sorry. 1, 0, 0. I hope this is right. So when you apply this tau function, you get this matrix, and based on what this is the weight table. So we need to weight in a clockwise fashion, starting from, I would say it as 10 o'clock. Okay. So we have this weight matrix 2 to the power 0, 2 to the power 1, 2 to the power 2, 4, 5, 6. Hope that's what they. Okay, fine. So what do we need to do? We just need to do a element wise multiplication of these two things. That's all we need to do. So whatever L, okay, let me just, yeah. So this LBP at location 2 comma 2 is this, where this is element wise multiplication. Okay, given this, what do we have? We only need to consider this and this. I hope you are able to see my pointer. Hopefully, yeah. So it's 2 to the power 1 plus 2 to the power 6, which is 2 plus 64. So your answer is 66. So yeah, for this matrix A, we have the local binary pattern given the central pixel is 66. Is this fine?
Yes, sir.
Okay. Yeah. Okay. Anything else that we have? Okay. This might be a good revision of linear algebra. So this is the last question for our session. So we are given two features, f as 32451 and g as 72532. So I'll denote each element as gi, or rather this is fi, this will be gi. Okay. So we need to compute the L1 and L2 norms. What is L1 norm? L1 norm of f comma g is what? Can anyone tell that? Absolute
Yes.
differences of the
Yeah.
elements, right?
Yes, sir.
Yeah. So it's minus 3 plus 0 plus 1 plus 1. It is 8. Okay. What about the other thing? L2 of f comma g?
Square difference of whole over 1/2.
Okay. That's all?
Whole 1/2 root, like square root.
Yeah. Square root of this. So that means we are just trying to square each of this and take the square roots. So it is 4 square plus 0 square plus 1 square plus 2 square plus 1 square. Okay, yeah. So this is what 16, 20, 22 square root of 22. Should be somewhere near what? 4 points this, right? Because we got 8. So it should be 4 points.
Yes, sir.
So this should be the answer. Okay, any doubts for today's session?
This week was completely about the only feature like detection and description. So we'll be like looking the map like whatever the descriptors we are storing, we'll then match it with the like if you want to detect the same point-to-point correspondence between two images, then we'll use the descriptors, right?
Yeah, yeah, we'll use these descriptors now to match. We have
Okay.
not done it yet, but we'll use that. So now once we have descriptors, now this L1, L2 norm, whatever you're seeing, we'll do some sort of uh, nearest neighborhood in these sense.
Okay. So
We'll,
the 128 number, like the 128 bit and all, will take help of that, right?
yeah, yeah, yeah. 128 dimensional features or other features, the binary feature LBP. Well, LBP, I don't
Okay.
think, it depends on what application you have. For the
Okay.
first thing, for homography and fundamental matrix, you need point-wise features. So for that, we'll
Yeah.
use mostly SIFT features.
Then after that, we'll be able to detect the same features.
Yeah, yeah. So if we now detect both the points, I mean images in both the points, and then match it, so we can detect now, given the lectures that we have done till now. The next
Huh.
week lectures will focus on matching. Once we have matched it, then you can do the usual homography or fundamental matrix or essential matrix estimation. So now the things
Okay.
get connected like this.
Yeah. Like this week, like it was really tough for understanding, like at once.
Oh yeah, yeah. No, that's okay. That's how we start to learn. Once you
Yeah.
learn it, it becomes easy.
Yeah. And the local binary pattern question was like at first I thought it was very tough, but once you did it, it was like so easy.
Mm-hmm. Okay, okay.
And the shift thing, I saw one like YouTube video in the morning,
Okay.
and he used the shift like he used an example where he had two images.
Yeah, yeah, yeah.
Why
Yes.
like
Yeah, okay.
okay, one image was having one book, but like where there was some labels on the like the book, and when he rotated the book to some like he rotated the book, and then he
Mm-hmm.
took another image, and then uh, the book completely it was like how can I say I'm not able to say that there in plane rotation was happening like the book was in planely rotated,
Okay, okay.
then also the shift detector detected all the feature points, so that was my doubt.
Yeah, yeah, yeah. Okay, yeah. I mean, yeah, it can happen, of course. See, book is a
Okay.
nice place to do it.
Plane, yeah.
If you want to do it in real life, that probably not city kind of places, but if you
Yeah,
want to
even he
go,
showed that also when like he took a 3D model like a 3D object, and then when he shifted like the when the extent like when the plane was the out when the out like the plane was shifted out plane, then it wasn't able to detect much features.
yeah, I mean, it depends on how things go, how complicated the structure is. So generally, I mean, SIFT it's pretty old now, but it's still the gold standard, I must say. There are variants of Swift. The basic Swift may not work that great, but variants of Swifts are still good enough, and they are competitive even to the current deep learning kind of methods. So,
Yeah. Okay. That's
so the whole thing here is that we are trying to get some description based on the image itself. So image just contains texture and all. If there is no texture,
yeah.
the texture varies too much, then it becomes not that easy to uniquely identify what's happening. So what you said is
Okay.
about feature matching. That if features are not matched properly, then all these things occur. Because feature detection is quite simple. Just need to create a
Yeah.
descriptor. The point is how good that descriptor is will then show up in the matching process.
Yeah. So if we apply point feature detector with if texture is there, then it will cause a problem.
Yeah, yeah, yeah.
Yeah. Now we got it. Thank you so much.
Okay. Anything else?
Yeah, that's all.
Yep. Okay, then I'll stop the recording.